Okay, let's get started. Are you recording my Facebook? Okay, hello everyone. Welcome to the Quantinuum workshop for iquhack 2023 Quantinuum Challenge. So first I'm going to introduce myself. I'm Catherine Spendy. I'm a quantum evangelist working at Quantinuum. And this is my colleague, Alan McPherson. He's working in quantum software and he specialized technical support and ticket outreach. Here are the emails. You can log down, or later you're going to see them online as well when we open up the challenges to get a hold of us, but we'll be around tomorrow during the hack time to answer questions you may have. Okay, so pretty much the content of this tutorial is part one, where I kind of go over ticket, features of ticket, which is our quantum software development kit Quantinuum has developed, and then how you use ticket in order to run your code. And specifically, we're going to go into mid-circuit measurement and Qubit reuse, which is a feature of our backend, which you will be exploring possibly in this challenge as well. And then QAOA, Callum is going to take over with that part. And please do interrupt me if you have questions, okay? So first of all, a quick introduction. We just want to a quick picture here about Quantinuum's full quantum stack. Pretty much what you're seeing here on top is our applications we have, and then ticket is kind of like the glue between the applications and then the hardware. And the nice thing about ticket, which is going to talk a little bit more about it, it is language agnostic. So it's language agnostic and also hardware agnostic. So ticket can be your gateway between, for example, if you use Qiskit or Q-sharp or Cirq, any kind of quantum SDK, you then use ticket, and then you can compile them, use ticket to compile different backends the most efficient way. And now we'll get into this. And more detail about Quantinuum is going to be during Mark Jackson's talk. He's in the back, our senior quantum evangelist on Sunday. So in any case, as you know, right now, we are in this noisy intermediate scale quantum era where you have not enough qubits to do something meaningful yet, right? Especially for error correction. And there's not enough, there are quite at 50 to 100 qubits to get to the point where they're enough to be hard to simulate classically. What you know when you work on a back end, right, on an actual quantum computer, is that every operation is noisy, right? Every gate you apply is going to add noise. You have to make a choice between 1 qubit gate and 2 qubit gates, right? 2 qubit gates give you 10 times more noise budget than single qubit gates, for example. So you want to always deal with noise. Qubits have a finite coherence time. Errors can vary across the machine, across time. They can be correlated. And the worst thing of all, sometimes errors are not very understood, so we can correct for them. So in any case, this is what we have. Given this, we have to make the best out of it. And this is where a ticket comes into play. So a ticket was developed with the goal in mind that we want to optimize in compiler to make it easy for people like you and me to use gate level quantum computers. And specific features of ticket that were at the beginning of development very much so put forward were that ticket should automatically handle many of the intricacies of the NISQ technology with the noise budget, for example. It should be independent of the language used to apply your algorithm. So you may have a favorite language you want to code in. So you should be able to use that. It should be independent of the quantum computer used to run the circuit. And it should free you as a user to get the best out of a backend, right? With not having too much work to do. So ticket is open source. And that said, you can download it from GitHub. And anyone can contribute too because it's open source. So we are looking forward to contributions for ticket. Okay, so this gives you an overview about all the extensions, some of them ticket has. So ticket pretty much, we have the C++ library, the core of ticket, that we call ticket. And then we have the Python wrapper, which we call byticket. So byticket is used for you. You code in Python that you can use the ticket library to compile your circuit in the most efficient way. We'll talk about this. And then we have front end and we have back end extensions Front end, for example, Qubit, Clipper, Python, physics, and then our back end, Quantinuum, IBM, we will be getting, and so on. So we have an extensive list. So as of now, in our counter today, I think we have 16 extensions that you can install and make use of. So Ticket is by far one of the most extensive quantum SDKs out there. And you should, you get to play with Ticket for this challenge, which is very cool. So obviously a Ticket was developed as a compiler in mind, right? So I'm not going to be able to go into too much detail, but pretty much Ticket we can focus on two things. You have circuit optimization, right? You want to preserve semantics of your circuit, but you want to make it smaller. So as you know, if you have two C0 gates applied, because unitary, they cancel out because they're an entity matrix. And then I told you before, for example, if you have 2 qubit gates, they're always more expensive than single qubit gates. So what you want to do is you want to maybe rewrite 2 qubit gates in a combination of single qubit gates, right? So anyways, these are ways of optimization. You're always going to want to do this because you want to decrease the number of gates you apply. And on top of that, you have to solve constraints, right? So you have different architecture, as you know, for your backend. Different qubits can talk to certain qubits, right? So if you have a chip, for example, the IBM chip, here's just as an example, you see that some qubits can talk to each other, but if you want to talk to this qubit, you have to go quite far, right? So you have to put in swap gates, and these are typically expensive. So again, you want to compile it the best way, and you want to do it the most efficient way. On top of that, what I don't show here, each of these qubits, even though I said your single qubit gates and 2 qubit gates have error, you're also going to have error because of these qubits being man-made, right? So there's each qubit themselves have an error. So it's an error budget. So when you have a circuit, right, you have an algorithm, you want to map it onto the IBM Eagle topography, for example, you'll make sure, for example, you use the qubits that have the least error, right? You also have readout error, you have spam, and so on. And then you have the gate sets, right? So each of these backends have a certain number of gates you can use. These are the basic gates. And for example, the Hadamard gate would have to be rewritten in this basic gate set because the Hadamard gate is not there, right? So this is something else. So a compiler like Ticket, our advanced quantum SDK, takes all this into consideration: the noise model, the basis gate sets, the topography, and also looks always for these kind of opportunities to make the circuit smaller. And that's what Ticket does. It's this package for you. You can apply, and it does it very efficiently. Okay, so installation of getting started with Ticket. It's a normal Python package. It's available free and set pip install PyTicket. And for this, if you choose to join the Quantinuum channel, you're also going to need pip install PyTicket Quantinuum. This is how you get access to our emulator. Then if pip install PyTicket Quantinuum, I did it twice. I'm sorry. It should be PyTicket Qiskit, which you're also going to need. Okay, so I'm going to make that correction in my notebook. So we're going to need the PyTicket Quantinuum extension and the PyTicket Qiskit extension. But we have other extensions which you can find in our documentation. Okay, if you're using Qubit, you know your own Python environment. I checked the PyTicket version 1.111.1 should be installed, and PyTicket Qiskit version 0.34 should be installed. If you want to check that you have these installed, you can also do a bib show PyTicket bib show at PyTicket Qiskit, and PyTicket Quantinuum extension you will need to install in Qubit, and you just as you do any kind of package, you can install PyTicket Quantinuum. This is perfect thing to do. Everything printed out when you install it. So anyways, these are the versions you need. So you need PyTicket, PyTicket Qiskit, and PyTicket Quantinuum. Okay, so how do you construct circuits? Oh, hold on. Yeah, that was it. So how do you construct circuits using PyTicket? For example, this is the basic gates for a bell state. We'll talk about that first. These are one of the 4 bell pairs. And if you want to code that in byte ticket, as you know, you can rewrite that into a bracket notation. And then you know that then you have your matrices. And based on the matrices, then you can write them in Hadamard, a Hadamard gate or a C0 gate. And obviously here you have the tensor product because it's a 2-qubit operation. The circuit class in PyTicket is pretty nice. And now I'm gonna actually go to the notebook if that's okay. So here you have the circuit class. I'm gonna make this a little bigger. Apologize. Okay, so here now, this is the PyTicket circuit class. So you import circuit, PyTicket circuit display, that's our rendering tool to make these very nice looking circuits. Then you define your circuit with the circuit class. So in this case, we are defining 2 qubits. And then we can apply the gate sequentially, which is really nice in PyTicket. So you're applying the Hadamard gate on qubit 0, and then you're applying the CX gate of, with qubit 0 and target qubit 1. Then you are rendering it with this very nice tool. And you may not notice this, recognize it at the beginning. It's actually ZX calculus version. Okay. So for those who use ZX calculus, and if you click here in the toggling, you can toggle between your regular presentation and ZX calculus presentation. How many of you have heard about ZX calculus? Some. You should read up on ZX calculus. There's a book coming out soon. And it's a very efficient way of doing circuit optimization and much more. Yeah?
Yeah, it's ZX. Zen. Please try to get more. Answer the question.
Compilation after and process, because all of these going to have at the back end, right? To understand our circuit, our back end, they have to do the compilations. Because the compiler code varies from the computing that the code is going to run on. So what should we use PyTicket to compile our circuit on our machine?
I think it's worth having optimizations that are available for the user to use in their Python environment so they can experiment with different optimizations and see what works well for them, because there are many optimizations available, and the order you apply those can be affect the result you get. And maybe you want to experiment and see if you can create your own optimization methods as well.
Right, but when they send your circuit to the backend, they do the optimization themselves before running the circuit, right?
Not necessarily, no. So you are submitting a circuit, right? And the backend compiles it the best. The hardware part, typically they have their own compiler. I agree with you. But if you're submitting a circuit with 100, I'm just saying C0 gates, right? Like random, you haven't really like optimized it. If the backend, if they don't have their own compiler, which you typically don't, would then implement all the C0 gates, for example, even if you could have less, right? So I'm just saying that typically you don't, the backends typically don't have their own compilers. It could be that they have their own compiler, but like Quantinuum does, so we have the ticket. So if you are submitting something to Quantinuum backend, it will be, we use ticket as our compiler. Qiskit has their own compiler, right? But instead of Qiskit compiler, you could use the ticket compiler. Okay.
Yes, it's always another circuit. So you're taking one circuit and you're trying to solve for the constraints of the device that you're targeting, and also trying to optimize it so that it performs better in the presence of noise. I would say it does both. I mean, there's complicated constraints that you have to solve for, like the hardware topology, like the physical layer of the qubits in the device. That's something that a compiler will have to solve for with adding swap gates or whatever, so that your algorithm is actually executable before you run it. Does that answer your question? Okay.
Yeah, we can talk about this later. Yeah. Okay. So given that you are applying, for example, this is the typical Bell state, that's our Hello World example, and you would like to run it on the Air backend, which is a Qiskit extension. I'm showing here now. So we are using the Air state backend in order to get the state vector. As you may use as a Qiskit user, we have the Air state backend. In this case, we are calling it with biQubit extension, .Qiskit. We are calling the backend here, defined as Air state backend. We run this is the circuit.run circuit, which we just defined above, and then we're going to get the .get state, the result from our backend. And this is we print the state vector here to go. So we 0, 0, 1, 0, and 0, 1, and then the 1, 1. And you can see here it's exactly what we would expect for this specific Bell state. There are many other gates you can use in tickets, just like in Qiskit, different gates, which you typically call in with the optype enum. Again, you can look in our handbook for details if you want to. This is just an example. For example, now where we have another circuit with a 3-qubit circuit. We are importing our optype here. You have the 1/2 rotation on the block sphere, so by 1/2 along the x-axis, the controlled RC gate, and so on. So in any case, you can build more complex circuits. And here again, this is the CX calculus recitation, and this would be a traditional circuit. We also have a download button here if you're interested to explore. So you can actually download your circuit, which is pretty neat. And save it. Okay. Next. You have also specific device-specific gates. What you're going to find for the Quantinuum backend is that we're going to have device-specific gates here, which is our CC phase, for example, and what else do we have here? CC max and phase dex. So in any case, if you compile to our Quantinuum backend, for example, you're going to see all these other gates pop up for your circuit. Okay. Anyways, there's many other gates, but we don't have time to go into all of them in this workshop. So let's talk about measurement. So if we talk about measurement, as you know, it's not show up now. Sorry. Yeah. So if you talk about measurement, you want to make sure that you are output. You take your qubit state, right, and then you want to measure it in order to get your classical qubits out, right, or bits out in this case. So we have a measure function in byTicket in order to get out the probabilities in form of all these state vectors, right? So, for example, if you want to know what the probability of the 0, 0 state is, typically what you do, you take a state function and you you square your factor here in front, your amplitudes, and that gives you the probabilities of a given state. And you can do that in a quantum compiler in a quantum SDK. But in this case, for tickets, you have to add here the measure all. In this case, you measure all of the qubits. You could be more specific for the measure function, which we're going to talk about a little bit. But in any case, when you actually run it on a backend and a real quantum computer, you want to make sure that you are measuring your qubits. In this case, you're measuring them in a C basis. That's why you have a little set C here. And here you have your classical register. So these are your qubits. That's your classical register. So you're measuring your qubits accordingly. So make sure that you always have this .measure all, for example, or .measure your given qubits, which we're going to talk about in a little bit. Okay, so we also have tools to move between Qiskit and ticket and Qiskit, for example. Here, for example, this you may sound very familiar with if you're a Qiskit user. This is the way you would code in Qiskit. And then if you want to move it into a PyTicket circuit, what you do is you import again your PyTicket extension of Qiskit, now Qiskit to ticket. So TK is for ticket. You take your circuit, your Qiskit circuit, you apply the function, and then you have a ticket circuit. And here again, you're measuring in this case, and then you do render circuit Jupyter again for our rendering tool. And you see that the circuit is here, which was before. So in any case, this is how easy it is to go between different languages, and you can apply it to other SDKs you're using. This allows you now to move your circuits around different languages. We also use support OpenQASM for storing and for uploading circuits. So here in this case, this is a Bernstein Vasirani circuit. And in this case, I had it stored on my computer in a QASM file. Again, I can do, if I take the QASM import circuit from QASM, I can also circuit to QASM, and I can also do a string version. In any case, it's always the same form. You call in the function, and then in this case, the QASM file, and then again render Jupyter, circuit Jupyter. And here is your circuit. So it's the different versions again, and that's your circuit. Okay. So now, if you want to run your code on a noise slit simulator, you can use the Qiskit Air simulator. That's a very nice simulator to use before to run on the backend. You kind of know what your result should be. This is a code we add, which is going to be in a notebook available online for plotting purposes. And here now you see we're running our bell state in this case, our circuit. On the air state backend, which we define here again, backend equals air state backend. And now we run it on the backend. We define the circuit, we define the number of shots, and we get the result. And then so our result counts, and then we plot the result counts here. So what do you expect? You get almost out of 1,000 shots. There should be variation between the two states, but they should be around 50% each. Okay, so one part of Quantinuum backend, what it is very good at doing is mid-circuit measurement and qubit reset. How many qubit reuse? How many of you have heard about this technique? Great. Okay, some not. So yes, good. So Quantinuum H1 device is very well. It's a unique feature of our platform, where we can actually take a qubit, measure it in the middle of a computation, and reset it in order to reuse it in later time. Why would you want to use that feature? Anyone? Huh? Save qubits, right? So if you have an algorithm that you can apply this methodology to, instead of like saying you have like a 40 qubit algorithm, right? But you only have 20 qubits you could use. If you can use qubit reset, mid-circuit measurement qubit reset, then you can have a wider circuit you can run on actually less qubits, which is great. Other things are error correction, for example, trying to read out the errors and so on. So mid-circuit measurement is very important for error mitigation and error correction as well. So this is a little circuit. So imagine here you have the circuit, right? And look at this one here. So this is a qubit, right? These are all 2 qubit gates here. But look at this qubit. So this qubit, pretty much nothing happened to this qubit here after this gray box, right? So you just do the whole algorithm, and then eventually when the algorithm is over, you're going to measure it out. On the other hand, you have this qubit here, or this operation, this C0 operation here, right? Which doesn't really happen till after this gray box. You see that? So this is gray box, where after this gray box, nothing happens to this qubit, and after this gray box, something happens to this qubit, right? So what you can do instead of like having 2 qubits here, what you can do is you can take the first qubit, you can reset it, you measure it, right? You reset it, and then you can use it for the next operation when it comes up. So now instead of having 1, 2, 3, 4, 5 qubits, I now efficiently only used 4 qubits. That's qubit reuse, mid-circuit measurement, and qubit reuse. That is what the crux is. So now, if you want to do this, and you want to, sorry, I'm going to try to put this over here. If you want to use this, so again, you have your circuit class and your op-type. In this case, we are having two qubits and 3 classical bits. We are applying a Hadamard gate to qubit 0. And now what we're going to do is we measure qubit 0 into the 0 bit. Okay, that's what this function does here. So we measure qubit 0 in the 0 bit. So if you now look down here, what you can see is that we have a Hadamard applied on qubit 0. Now we measure qubit 0, right? Now, after we measured it, we're going to reset that qubit 0, which this function. So now we're resetting it. And then we are applying a C0 gate right here. And then again, later we measure out qubit 0 again, but now in bin 1, classical register 1. And we are measuring qubit 1 in classical register 2, right? So we had now 3 registers, classical registers, 0, 1, and 2 qubits. Okay, so we have to have more classical registers in this case than qubits. So this is how you set it up, and here's the circuit rendering. So you should be clearly seeing a reset if you apply this, right? So you know what is it all about. So now going back to the Bernstein-Masirani algorithm, it turns out that for this algorithm, we can do this very nicely. So here is your algorithm. Okay, so probably that. So you see here, you have a Hadamard gate, a couple of C0 gates, and that's how we measure it out. But if you look very closely, you see something happens here, right? I'm measuring out, and then nothing happens here. You see that? So you can actually use this real estate here to have qubit resets. And now I'm going to show you for this specific circuit how you do this. So first of all, we want to, maybe it's better if I look. So this is the coding I'm doing here. So pretty much, again, measuring it out and resetting it. So when you have time, you should go through that code. But the important part here is here, what I want to show you. So here now, I'm able to do this first part here, right? You see? And then I have nothing else happen for this qubit afterwards. So now I can reset the qubit, and I can use it for so qubit 0 I reset, and now qubit 0 became a qubit 1. Okay. And similar now, if you look here, after my qubit 1 was implemented, now I'm realizing there's something happening to qubit 2, right? After qubit 1 is used. So I can also reset qubit 2, qubit 0 one more time, which I'm going to do here. You should go through the code then. And then you see here what happened. Again, now I'm resetting qubit 0, and qubit 0 now became our qubit 2. And pretty much reset qubit 0 2 times, once in order to do what happened on qubit 1, and the second time in order what happened on qubit 2. So what I did now efficiently is 1, 2, 3, 4, a 4-qubit BV algorithm I rewrote into a 2-qubit algorithm, which is pretty powerful, right? So if you would have only a hard backend that has 2 qubits, you could run this algorithm now with using mid-circuit and qubit reset. So in this case, we had a 50% usage. We've saved 50% of resources, right, with this method. And it turns out that you can do an n-qubit BV algorithm, always on 2. You can have like a 100-qubit BV algorithm. You always can put it onto 2 qubits if you use mid-circuit measurement and qubit reuse. But obviously, you know, you add gates, right? So it's expensive, and you're going to have error you have to work with. Okay, so now we can talk about analysis tools for our algorithm. So Ticket has a lot of analysis tools we can use. For example, our first, I apologize here for this being, I don't know if I can move it. Yeah. So for example, our first PV circuit, we can ask how many gates did it have? 14. How deep was it? It's 7 layers, and how many CX gates did it have? So this is the way of like you can actually ask number of gates, dot the depths, and then of the uptype, you can define whichever gate you want to count. Now, after we reused one, we did one qubit reuse method. You can see now the number of gates increased, right? Because we had to do a measure function, right? That's one gate, that's one operation. Now the circuit depth increased, right? Because we're adding it to that 0 qubit. CX gates stay the same. And then if you look at our last operation where we did 2 mid-circuit measurements and qubit reuses, you can see again, we increased the number of gates, we increased the number of steps, we keep the CX gate the same. So you are gaining in resources, right? Being able to use less qubits, but you are adding in the depths of the circuit. So it's not a win-win situation, right? So you have to figure out what works best for you. Okay, so what you're gonna do for the continuum challenge, you're actually gonna submit it to the emulator, which is a 12 qubit emulator. Our emulator is, it's a cloud-based emulator you can access. You're gonna do this through a Quantinuum user portal, which I will set you up with for an account. Our emulator has the noise and all the models of our backend. In this case, our 12 qubit machine. So it's a very ideal emulator for a quantum device. Our quantum devices actually don't run on the weekends because they're located in Broomfield, and we run them during the business hours during the week. So the emulator is what we can make available for you here. But pretty much it has all the functionalities. It has the correct error model. It has qubit measurement, qubit mid-circuit measurement, and qubit reuse, and all the other functionalities of our backend. Okay, so using the emulator will give you a good idea of what you can actually run on our actual backend. So it's a H1 2E emulator. Mm-hmm. Yeah. Yes, so we are.
I would say more that it uses a sort of approximate noise model. It's informed by real parameters of the device, but it's as a model rather than directly from the device. That's my understanding.
Yeah, and so it has the Q, for example, the qubit error rate, the readout error rate. So you can measure very precisely in the actually from a computer, which is something that you can very well calibrate. Then obviously some errors, which I talked earlier. There's some errors that we are not well understood. Some things we can't really model yet. But it's a very good estimate. Yeah. So again, you need to pip install PyTicket for this. PyTicket Quantinuum. And this is how you're going to access the emulator again with the extension, the Quantinuum backend, H12E, that's the emulator. And then in this case, this is how you call it. And then when you actually want to run the emulator, you have to sign in to the backend, which will prompt you for your email and your password, and you will be setting this up. So if you do the Quantinuum challenge, you'll be setting up this account, and I will be the point of contact and also Column, but more so me, in order to get this started when you have problems with sign up. Then circuit compilation. So we didn't have much time to talk about circuit compilation, but Ticket includes many features of circuit compilation. There are many passes that can be done for Ticket. If you want to learn more, please look at the manual. But pretty much for the purposes of this challenge, to get you started, what you can use is you can use our default compiler pass, which is called get compiled circuit, which you're going to apply here. You input the circuit and you input the optimization level. If you leave this blank, optimization level default is 2. where level 0 is solves just the constraints for the device without optimizing. Level 1 is like some light optimization. Level 2 is some more optimization. If you're interested in all details, you click on this link then when the challenge is available, and you will have the list of compiler passes we apply for the Quantinuum backend. And each backend has their own compiler passes that work best for the backend, which kind of like is this done on random circuits when you define the compiler passes that work best?
It's done by experimenting with different benchmarking
circuits
and see what works best. And then we define a custom sequence of optimizations that's tailored for the specific devices that you can access through the different packet extension modules.
Mm-hmm. Okay, so here now I'm showing you the BV algorithm again. Trying to open this up here. So this is our BV algorithm, which we did. We applied mid-circuit measurement twice on. You can see here we have two Quantinuum now. Our gates here, our qubits, sorry. And these are the device-specific gates for the Quantinuum device. And again, here you see the mid-circuit measurement and reset. Okay, this is your circuit now. After you compile it, and we used level 2. Again, you don't have to set that optimization level to 2. This default is 2, but I just wanted to show you here how you can change the level. And then if you run it on the backend, this is your call, how to run it. Again, it will be available in Notebook for our challenge. You can check the status of your job. It is an emulator. It is cloud-based, so you're going to be queued. So keep that in mind when you do a challenge. Okay, there's going to be a queue. Don't last for the last minute to get your result. You can check the status. It shouldn't take too long. It's typically done in like a minute or so, right? You can retrieve your results if you wanted to. And here, this is the result for the emulator, right? So in this case, 111, it's the ideal result. And you can see that we did a pretty good job with 490 out of 500 getting in the right state. If you want to check for your challenges, this is how you can save your results. If you wanted to with a JSON file, give you the thing here too, and how you can get them back, your results. It's for later use if you want to save it, if you don't want to write the result down right away. But if you want to run your circuit on a noiseless simulator, again, just use the AIR backend with this code here. And you see that the 1110 state is indeed the one they should be getting. Okay. So in any case, if you experiment with mid-circuit measurement and qubit reuse, you can also use a classical simulator, in this case, the AIR backend, in order to figure out if you did a good job, okay, what you should expect. Okay, so that now brings me to Callum.
Yeah, thanks, Catherine. You have until past.
Yeah, we have a little longer because we started late.
Oh, yeah.
Is that it? I have to stop sharing.